Okay, we have Julia Haynes from UCSD.
Hi everyone, my name is Julia Haynes and I recently finished my Data Science Master's program at UC San Diego earlier this year. I've been working with Professor Adam Bergasser at the Cool Star Lab for this last year. And we have been working with collaborators on a project I am really excited to talk to you guys about today, using variational autoencoders to accelerate atmospheric analysis for brown dwarfs. So Roman is expected to find thousands of brown dwarfs, and that is really exciting because often with more data, we have more discoveries. We want to use brown dwarfs to understand the Milky Way because they are abundant, they live forever, and they evolve with time, which makes them really good, really good for understanding the Milky Way. However, to do so, we need to understand their individual atmospheres. So, however, atmospheric analysis is extremely computationally time-consuming. So, interpolating grid models and computing new models are the rate-limiting steps in atmospheric analysis. So, for example, for the brown dwarf atmospheric model Sonora Diamondback, it takes 27 minutes to generate 10,000 models via linear interpolation. And then it takes 70 minutes to conduct a fit with MCMC. So we are already at our computational limits with JWST data. It took one of my collaborators several weeks to fit 11 different models onto 60 different sources. And so when we think of the influx of data that we will be getting from Roman, we really need to find ways to accelerate atmospheric analysis. So to address this, my group explored using variational autoencoders. So variational autoencoders are a generative neural network, and it essentially compresses input data and regenerates new data from the input data. So I'll first define latent variables, which are variables that are not directly observable, but they still represent and describe the data. So essentially, during training, the encoder maps the data to a lower dimensional latent space, and the decoder recreates the data from the latent variables. The latent variables are described by a mean and standard deviation, which allows it to generate data in between the training points. The model optimizes a loss function that includes the mean squared error and the KL divergence term. So the KL divergence term is really neat. It's able to quantify the difference between a distribution to the standard normal distribution. And the larger this difference is, the larger the KL divergence term becomes. And so by including this into the loss function, we're able to ensure that the data generated in between the training points make physical sense. So conditional variational autoencoders are slightly different. They are an extension of variational autoencoders, but essentially they take in parameter values along with the training data, and this allows the parameter range of the generated data to be controlled. So the parameters are mapped on to the input data before being fed into the encoder. And the parameter values are again mapped onto the latent variables before being fed into the decoder. And in a very similar astrophysical use case to this project, Gibran and Bentley in 2025 used conditional variational autoencoders to generate stellar spectra. Had they used a regular variational autoencoder, they wouldn't have been able to control the stellar parameter values. So we trained a conditional variational autoencoder on the Sonora Diamondback model grids. I'll be showing fits to JWST because we don't yet have Roman data, but I will show some models generated for Roman. So during training, we input our spectra along with the parameter values. The encoder learns a lower dimensional latent representation of the data. And the decoder takes this lower dimensional latent representation along with the parameter values and reconstructs the original spectrum. So with each iteration, the reconstructed spectrum is being compared to the input spectrum via mean squared error, as well as the latent variables are being, the difference between the latent distribution and the standard normal distribution is being quantified via the KL divergence term. And the model updates accordingly. So in total, the training time took 5 minutes. So after we trained the model, we were able to use the conditional variational autoencoder to generate new spectra. So we were able to do this by inputting a parameter range, and for each grid, we sample a random Z, and the coder takes this and generates new synthetic spectra. So each spectrum took about 0.3 seconds to generate. We are able to control how dense the grid is by choosing the number of values for each parameter. So the denser the grid is, the better fit we can make with it. However, the denser the grid, the longer it takes to generate, and the longer it takes to actually make the fit. And so in order to keep this from being a computational bottleneck, we explored fitting multiple grids. So first, a very sparse grid that took a couple seconds to generate and fit. And then based on that fit, we then generated another much more dense grid, but with a much smaller parameter range. And so with that, we were able to make accurate fits. So here are some of the models generated for the Sonora Diamondback model grid for JWST. The temperature is, the parameters except for temperature are fixed, and the temperature ranges from 900 degrees Kelvin in purple at the bottom to 2,400 degrees Kelvin in the yellow at the top. And we were able to generate 10,000 spectra in 1.6 seconds, which is 1,000 times faster than linear interpolation. And here are some of the models generated for Raman prism data. The spectra for Raman took about 1.5 times longer to generate. It was 0.45 milliseconds per spectrum instead of 0.3 for JWST. And similarly to the last plot, the parameters except for temperature are held constant, and the temperature ranges from 900 degrees Kelvin to 2,400 degrees Kelvin. And we are very excited to make fits on Raman data. So going back to our Sonora Diamondback JWST model, we compared a MC-MC fit made with the original model grid to a VAE grid fit. So we were able to compare these because the VAE grid is very dense, and the uncertainty values for both models fall within the ranges of one another, and so these models are statistically consistent. The MC-MC fit returned a temperature of 2,249 degrees Kelvin and a log G of 4.23 and a metallicity of negative 0.35. The VAE fit returned a temperature of 2,243, a log G of 4.23, and a metallicity of negative 0.38. So these fits are very close to one another. They only differ by a temperature of 6 degrees Kelvin and a metallicity of 0.03. And the chi-squared values are also the same at 1.8. The MC-MC fit took 70 minutes, while the VAE grid fit took only 6 minutes. So this is a speed up of over 10 times. And interestingly, we actually conducted a MC-MC fit with the VAE grid, and we actually obtained the exact same fit, including chi-squared. And so this further validates our VAE grid. So for next steps, we want to train the model on all Braun-Dwarf atmospheric model grids, and we want to include a framework that allows anyone to train a conditional variational autoencoder onto any atmospheric model grid. And we want to explore incorporating variational autoencoders into the MC-MC framework. And we want to explore applying this to random forest retrieval frameworks as well as atmospheric retrievals. So here are my key takeaways. So variational autoencoders accelerated the model generation process for the Braun-Dwarf atmospheric model Sonora Diamondback by over 1,000 times. After training for 5 minutes, performing a fit with the variational autoencoder grid showed evidence of being faster than running an MC-MC fit. We will explore applying this to retrieval frameworks as well as MC-MC, and apply this to other models for Roman prism and GRISM modes, as well as other fitting frameworks beyond MC-MC. Thank you. I'll take any questions.
Okay, do we have any questions? Jessica?
Nice talk. I was wondering why the variational autoencoder uncertainties were so much smaller than the MC-MC version.
That's a great question. I'm not sure if I can answer that right now.
Hi, this is really nice. Model fitting takes a long time. Do you intend to make this open source, or can it be adapted to other instruments, say Spherix or Euclid?
We definitely plan to make this open source, and yes, it is definitely applicable. Yeah, that is something we're currently working on.
And
yeah, thank you. Great talk. If you just go back like 2 slides, I wanted to see the one, sorry, the next steps one. Yeah, thank you so much. Yeah, I think a similar question to the question in the back. I was just curious, like when you say a framework that allows anyone to train on any model grid, like how would that work? Like you would go to GitHub and pull it, or how would I use it personally and adapt it to my own model grid?
Yeah, so our Professor Adam Vergessen, he created UCD MC-MC, an atmospheric model fitting package, and so essentially, yeah, it would be from GitHub, and the framework would be on that, in that code.
Thank you.
And then I'll take chair privilege. This was a wonderful talk. May I ask you, can you give me a feel for dimensionality here? Because when you talk about, allowing for variation when you're first trying to generate these models, right, in temperature, your temperature range that you span is how big? And then also, what are the steps in temperature?
So I don't know if you remember, I was talking about creating like 2 different grids. So the first grid is very sparse, so it ranged from 900 degrees Kelvin to 2400 degrees, and then I believe it was about every 25 degrees, that was the step size. And then for the much more dense grid, it was a much smaller parameter range, so I want to say like between like 2,200 and 2,300, and the step size was every 1.
Okay.
There's one question.
Oh, yeah, please.
Hi. I assume when you generate those spectrum, you know a ground truth temperature. How is the fitted temperature from VAE MC-MC compared to that ground truth?
ultimately pretty well. But yeah, I would need to do more comparison to give you an exact answer on that. Faster.
All right. Well, thank you very much. And now can we have our next speaker, please?